Hey everyone, welcome back to Fuzzy Logic Lectures. In the previous lecture, we learned few important concepts of classical logic like proposition, connectives and tautologies. In this lecture, we will look at the remaining concepts, that is contradiction, exclusive or and nor, and logical proofs. So let's get started. First, let's take a look at contradiction. I hope you all remember the definition of tautology as per the previous lecture. We learned that a tautology is a compound proposition that is always true no matter what the truth values of the individual propositions that occur in it is. Now, contradiction is the exact opposite of a tautology, as in, a proposition that is always false regardless of the truth value of the individual simple propositions constituting that compound proposition is called as a contradiction. We saw that the truth table for a tautology had true or T in every row, right? Now, a truth table for contradiction on the other hand will be having false or F in every row. For example, if we take A intersection A bar, we will get it as phi. Now, phi is a null set which is false or it has 0 as all its elements. Similarly, if you take B intersection phi, we will get it as phi. Now this again is a null set which is depicting false. So this is how you depict contradiction, or this is how it appears. So let's take an example to prove a given proposition is a contradiction. The question given here is to build a truth table to verify that the proposition P equivalent Q conjunction P bar conjunction Q is a contradiction. So let's take the truth table. In the truth table we have P, Q, P bar, P equivalent Q, P bar conjunction Q, and finally we have P equivalent Q conjunction P bar conjunction Q. So let's put the values as true, true, false and false. We have true, false, true and false. Now for P bar, now the negation of true is false, false, negation of false is true and true. For P equivalent to Q, if both are true and if both are false, it will be true. Rest conditions, it will be false. Then for P bar conjunction Q, we have to take these two columns. So we have false, false and false will have false, true and true will have true, false and true will have false. Then lastly, we have to take P equivalent Q conjunction P bar conjunction Q. So we have true and false, which is false, false and false, which is false, false and true, which is false, and true and false, which is false. That is, we can see that the final value of the compound proposition is false and hence it is a contradiction. So this is how you prove that a given proposition is a contradiction. Moving on to exclusive or and nor. As I've mentioned in the previous lecture, exclusive OR will output a true value if exactly one of the two conditions is true but not both of them. For example, if you have two single propositions A and B, then exclusive OR will output a true value if only A is true or B is true, but it will output a false value if both A and B is true. So let's take a look at the truth table for exclusive OR. Here we have P, Q, and P XOR Q, which is your exclusive OR. So we can write it as true, true, false and false. Here we'll write true, false, true and false. Now when you take P XOR Q, I have mentioned here that it will output a true value if exactly one of the two conditions is true but not both of them. So if both are true and both are false, it will give a false value because only one of the conditions need to be true. And the rest two conditions, it will be a true value. So this is the XOR's truth table. Coming to exclusive NOR, we can say that exclusive NOR is the complement of exclusive OR. For example, if you have two single propositions A and B and we are taking the exclusive OR of A and B, then you can say that exclusive NOR will be the negation or the complement of exclusive OR. Therefore, A XOR B, the whole negation, will give you your XNOR or your exclusive NOR. So let's take a look at the truth table of exclusive NOR. So here we have P, Q, P XOR Q, the whole negation. Now as we've seen earlier, we'll put this as true, true, false and false, and true, false, true and false. Now since I've mentioned that exclusive NOR is the complement of exclusive OR, what we get over here, it will be the reverse. As in here it will be true, here will be false, false and true. That is, if both the conditions are true and if both the conditions are false, then P XNOR Q will be true and in the other cases it will be false. So this is how you do exclusive OR and exclusive NOR. The last concept which we have is logical proofs. As we have already seen before, logic is the ability of humans to reasonably think about something and make a decision based on some proofs. Now what exactly is a proof? A proof is an argument from a hypothesis which is an assumption to a conclusion. Each step of the argument follows the laws of logic, and a statement is not accepted as valid or correct unless it is accompanied by a proof. Now if we are given a hypothesis or a statement, then we can often make certain conclusions from them. Now in the case of logical proofs, we have certain steps for that. First, what we do is that we analyze a given compound proposition which is given in the form of a linguistic statement. Now a linguistic statement is just a statement that is written in the form of words as per the English language. As we have seen earlier, propositions are represented by capital P, capital Q or by variables. Now a linguistic statement will be having actual words and sentences. Now the second step is we are going to decompose this particular statement into single propositions. And then we have to express the statement algebraically with all its logical connectives in proper place. And finally, we have to verify the truth value of the statement with a truth table. Now I understand that these steps might be a little confusing for you to grasp quickly. So let's take an example to see how logical proofs work. In this question, we are provided with a hypothesis and a conclusion. In the hypothesis, it is a combination of three statements, the first being scientists are mathematicians, logical thinkers do not believe in magic, and mathematicians are logical thinkers. In the case of conclusion, we have scientists do not believe in magic. Now what we need to prove is, we need to prove that for a given hypothesis and conclusion, the given statement will have a true value. So for that, according to the steps that I have mentioned earlier, we have first analyzed the given proposition which is in the form of a linguistic statement. As you can see, these are in the form of a linguistic statement. Now the next step is, we have to decompose the statement into single proposition. So to decompose the statement into single propositions, let us consider four variables P, Q, R and S, where the proposition P represents a person is a scientist, Q is a person is a mathematician, R is a person is a logical thinker, and S is a person believes in magic. Now going back to the steps, we can see that the next step is to express the statement algebraically with all its logical connectives in proper place. So what we need to do is, we need to express these statements in an algebraic manner or an algebraic expression. In the hypothesis, the first statement is, scientists are mathematicians. Now we know that P represents a person is a scientist and Q represents a person is a mathematician. So here we can say that scientists are mathematicians, which means that scientists are implied to be mathematicians. Therefore, we can see that we can write it in the form of P implies Q. Why? Because P stands for a scientist, Q stands for a mathematician, and here it is given as scientists are mathematicians. So, for the first sentence, this will be the algebraic expression. In the next statement we have, logical thinkers do not believe in magic. We can see that R is a person who is a logical thinker and S is a person who believes in magic. So we write it as R and S. But according to the statement, we can see that logical thinkers do not believe in magic. Now since S is a person who believes in magic, if you take the negation of S, we will get a person who does not believe in magic. So we can write it as R implies S, which is logical thinkers do not believe in magic. That is, logical thinkers are implied to not believe in magic. Therefore, R implies S bar or S negation. The next statement we have is mathematicians are logical thinkers. Now, mathematicians are represented by Q and we have logical thinkers which are represented by R. So here we can say that mathematicians are implied to be logical thinkers. Therefore, Q implies R. Lastly, our conclusion is given as scientists do not believe in magic. So scientists are represented by P and a person who believes in magic is represented by S. So a person who does not believe in magic is taken as S bar or S negation, and you can write it as P implies S bar. Now we need to form a proper expression with putting the correct logical connectives in place. Now an important thing here to look is, since all these three statements they make up the hypothesis, we have to consider the combination of these three statements to prove for the given conclusion. Hence we use the conjunction connective for this purpose. That is, here we have P implies Q, conjunction, R implies S bar, conjunction, Q implies R, and this whole thing is your hypothesis. Now the hypothesis will imply the conclusion, therefore you will have the implication operation and you will have P implies S bar. Now an important thing to note here is that we can't use the disjunction connective because in the disjunction or the OR connective, not all of the statements in the hypothesis are required to prove the conclusion. Only one or two of them is required. But to check the truth for a given statement, it is crucial to prove the entire hypothesis and the conclusion as true. And that is why we are considering the conjunction connective. Now the next step what we have to do is, we have to verify the truth value of the statement with a truth table. So let us verify the truth value of this expression with the help of a truth table. And then we can prove that a given statement is true or false. So as you can see here, I have a truth table and I have our expression. I have also put the values as P, Q, R, S, S bar. P implies Q, R implies S bar, Q implies R and P implies S bar. Now for my convenience, I have depicted this part of the expression, that is P implies Q conjunction, R implies S bar conjunction, Q implies R as variable X. And I have depicted this entire expression as variable Y. So now that we have all our values set, let us try to find out what is the final truth value of the given statement. So we have a total of 4 variables. Therefore, we have 16 different possible combinations. So let us find out the truth value for the statement. So initially we have S bar, that is your S negation. So we have to take the negation of the values in S. So true's negation is false, false is true, true is false, false is true, and similarly. Next we have P implies Q. That is, we have to consider the P column and Q column with the implication operation. So we know that true and true will be true. Similarly, then we have true and false, which will be false. Then we have false and true, which is true. And lastly, false and false, which is again true. Next is R implies S bar. That is, we have to consider the R column and S bar column with the implication operation. So first we have false, because true and false will be false. Then we have true. False and false will be true. False and true will be true. Similarly, we have next we have Q implies R. That is Q column and R column with implication operation. So we have true and true, which is true. Then true and true again, which is true, false, false. Similarly, next we have P implies S bar. That is, you have to consider the P column and S bar column with the implication operation. So first we have true and false, which will be false. Then we have true and true, which will be true. Similarly, we have Next we have the variable x, which is given by P implies Q conjunction R implies S bar conjunction Q implies R. So we have to consider these three columns, that is P implies Q, R implies S bar and Q implies R with the conjunction operation. So first we have true, false and true, which will be false. Then we have all trues, so it will be true. Similarly, lastly we have variable y, and we know that y is given as the whole expression. That is P implies Q conjunction R implies S bar conjunction Q implies R. The whole thing implies P implies S bar. That is, we can consider the x column since x represents this, and we can consider this column, that is P implies S bar. So we have to take false implies false, which will be true. True implies true, which will be true. Similarly, since we can see that the final result or the final values all are true, therefore the given statement will be true as per logical proof, or we can say that the given statement is a tautology because all the values are true and hence it is proved. Now let's solve another question with logical proofs. In this question, we are given a hypothesis as if you score 95% and above, your success is represented by a good grade. And the second hypothesis is you scored 95% and above. And the conclusion is given by your success is represented by a good grade. Now for logical proofs, like I said earlier, the first step is to break down the statement into its individual propositions. So here I have broken it down as P and Q, where P is you scoring 95% and above and Q is your success is represented by a good grade. Next, we have to express these statements as algebraic propositions with the required connectors. That is, as per our first hypothesis, it is given as if you score 95% and above, your success is represented by a good grade. Now we know that P implies Q is generally given or represented in the form of an if-then statement. That is, if P, then Q. So our P is given as you score 95% and above, and Q as your success is represented by a good grade. Therefore, you can write this statement as P implies Q. Now the next statement or the next hypothesis is you score 95% and above. So, you score 95% and above is represented by P, and as I said earlier, you have to use the conjunction operative because you have to include both these statements in your hypothesis. So you have the conjunction operative and you have P, because our second hypothesis is you score 95% and above represented by P. Then we have this implies our conclusion. And what is the conclusion given by? The conclusion is given as your success is represented by a good grade. And here Q is representing your success, which is represented by a good grade. Therefore, you write it as Q. And therefore, we have our algebraic expression as follows. Now, the next step is to construct a truth table so you can verify the truth of the statement. So, here we have a truth table. We have P, Q, P implies Q conjunction P, and P implies Q conjunction P. The whole thing implies Q. So, let's fill it. We have true, true, false and false, true, false, true and false. First we have to take P implies Q, that is this column and this column. So true implies true, which will be true, true implies false, which will be false, false and true will be true, and false will be true. Then we have P implies Q conjunction P. So you have to consider this column and this column. So true and true will give us true, true and false will give us false, false and true will give us false, and false and true will give us false. Lastly, we have P implies Q conjunction P, the whole thing implies Q. That means we have to consider this column and this column. So we'll take true implies true, which is true, false implies false, which is true, false implies true, which is true, and false implies false, which again is true. So as you can see, we have the final value of the compound statement all true, and therefore it is a valid statement and hence has been proved. Now, an important thing to note is that sometimes certain statements or propositions will be very difficult to prove by this direct proof. So, in such situations, we use indirect proofs, as in indirect proof. Now, generally in indirect proof, we use the method of proof by contradiction. Now, what this means is that we use it in those cases where we state that a statement is true only if its alternate statement is false. So, if we want to show that a compound statement is a tautology, we can alternatively show that the alternative statement is a contradiction. So, this is how you do proof by contradiction. Let us consider the same example as we have seen over here. The expression which we have obtained is P implies Q conjunction P, the whole thing implies Q. So, let us write it down here. We have P implies Q conjunction P, the whole thing implies Q. As per the previous lecture of our fuzzy logic playlist, I have explained that P implies Q can also be written as P bar union Q or P bar disjunction Q. If anyone has any doubts, please refer the previous lecture and I have included the link in the description below. So we can write P implies Q as P bar disjunction Q or P bar union Q conjunction P, the whole thing implies Q. Now I can expand this again with implication, as in this term implies Q. So I can write it as P bar disjunction Q conjunction P, the whole bar disjunction Q. And let's put this as expression 1. Now, as per proof by contradiction, we have said that a statement is true only if its alternate statement is false. Now, to find out the alternate statement, we have to take the negation of the actual statement. So, here we have to take the negation of equation 1. So, what we do is, we will consider the negation of equation 1, which is given as P bar disjunction Q conjunction P bar disjunction Q, and we have to take the whole bar because we are taking the negation. So, when we simplify this, we get it as P bar disjunction Q conjunction P. Now, since this negation, disjunction will change into conjunction and we'll have it as Q bar. Now, this becomes our alternate statement. So, if the alternate statement is false, or if we prove that the alternate statement is false, then we can say that the original statement or expression number 1 is true. So, this is proof by contradiction. So, let's consider the truth table to prove that. So, here we have the truth table and let's fill in the values. We have true, true, false and false, true, false, true and false. Then we have to take the negation of P. Just P negation, true's negation will be false, false, true and true. Similarly, take negation of Q, we'll have false, true, false and true. Next, we have to take P negation disjunction Q. That is, we have to consider this column, disjunction, this column. So, we have true, false, which will be true, false, false, which will be false, true, true, which will be true, and true, false, which will be true. Then we have P negation, disjunction Q, conjunction P. That is, we have to consider this column and this column. This column, conjunction, this column. So, we have to take true and true, which will be true, false and true, which will be false, true and false, which will be false, and false and true, which will be false. Lastly, we have P negation, disjunction Q, conjunction P, the whole thing, conjunction Q negation. So we have to consider this column, conjunction, this column. So we have true and false, which will be false, true and false, which will be false, false and false, which will be false, and true and false, which will be false. So as we can see that the given statement is a contradiction because all the values is false, and therefore our original proposition or our original statement is true. So this is how proof by contradiction works. I hope these methods are very clear to all of you. If any of you have any doubt in any of the methods taught in this lecture, please feel free to ask in the comment section below. Either we or another viewer will surely help you out. If you found this video to be useful, please like this video and support us by subscribing to the channel. In the next lecture, we'll be continuing with classical and fuzzy logic, where we will be discussing about connectives, tautologies and propositions when it comes to fuzzy logic. Thank you for watching properly and have a great day.